Picture walking a bumpy road, eyes closed. Your feet tell you 3 spots are perfectly flat, all 3 identical. But one is the top of a hill, one is the bottom of a dip, and this middle one is strange. It pauses flat, then keeps climbing the same way it already was. If flat is all you can feel, can you actually tell which is which? Keep that road in your head, we're coming back to it. You already know a flat spot means die/dx equals 0 there, and that die/dx itself can be differentiated again. Real question. As this dot climbs toward the top of the hill and over it, is the gradient number getting bigger or smaller the whole way through? Watch the number. It counts D, O, W, and the whole climb, positive, shrinking, 0 at the crest, then negative. That falling trend is exactly what the second derivative measures. Give the 2 bends a name. Bend like the inside of a cup, opening upward, that's concave up. Here's how to spot it. Slide a tangent line along a concave up stretch, and it always tucks in under the curve. Bend like a dome or a cap, opening downward, that's concave down. Slide it along a concave down stretch, and it always sits above the curve. 1 sentence each. If the gradient is climbing through the flat spot, that climbing rate, the second derivative, is positive, so concave up, a cup. If the gradient is falling, it's negative, concave down, a cap. You don't need the picture once you have that number. The sign tells you the bend. Here's how you'll remember this forever. A positive second derivative smiles, a happy little cup, and a smile at a flat spot means you're standing in a valley, a minimum. A negative second derivative frowns, a sad cap, and a frown at a flat spot means you're on a hilltop, a maximum. Say it with me. Positive smiles, that's a min. Negative frowns, that's a max. Start with y itself. Bring the power down, drop it by 1. That gives die by dx. Now take die by dx itself and run the exact same rule on it a second time. Bring the power down, drop it by 1. That gives d squared y by dx squared. One trap. To get the second derivative, do n, o, t go back to y and try something new. Same rule, applied twice in order, or you'll land on a wrong expression. Quick guess. If the second derivative comes out to exactly 0 at a flat spot, is that automatically a maximum, a minimum, or something else? It means the test failed to decide, that's all. Go back to die/dx and check its sign just before and after the point. If the sign stays positive or negative, both sides, you're not on a turning point. It's a point of inflection with a horizontal tangent. The curve paused, then kept going the same way. Back to our road. Same 3 flat spots, same identical feeling underfoot, but now we have a number for each. Guess this one first. Frowning, second derivative negative, that hilltop is a maximum. This dip, smiling, positive, a minimum. That middle shelf, second derivative 0, test fails, check die/dx either side, never changes sign, confirming a point O, F inflection, not a hill or a dip. Given y equals x cubed minus 3x squared minus 9x plus 5, find the stationary points, and, using the second derivative, determine the nature of each. Differentiate term by term, set die over dx to 0, and factorize to find the stationary x values. X equals 3 or negative 1. Differentiate die over dx again, not a fresh rule on y, to get the second derivative, 6x minus 6. Test each x value. At x equals negative 1, it's negative 12, concave down, a maximum. At x equals 3, it's positive 12, concave up, a minimum. Substitute each x back into the original curve y, never into die over dx, to get the matching y coordinates, 10 and negative 22. Stationary points at minus 1, 10, and 3, minus 22. At x equals negative 1, the second derivative is negative 12, less than 0, so minus 1, 10 is a maximum point. At x equals 3, the second derivative is 12, more than 0, so 3 minus 22 is a minimum point. Given y equals x cubed minus 6x squared plus 12x plus 1, find the stationary point and determine its nature, showing your reasoning if the second derivative test doesn't decide it. Differentiate to get 3x squared minus 12x plus 12. Factor out the 3 first, leaving x squared minus 4x plus 4 inside the bracket, and that inner bracket is a perfect square, x minus 2 squared. So die over dx is 3 times the bracket, x minus 2 squared. Setting it to 0 gives one stationary value, x equals 2, a repeated root. Differentiate die over dx again, 6x minus 12. Add x equals 2, that's exactly 0, so the second derivative test fails to decide. Fall back to the sign of die over dx itself. A positive constant times a square, never negative either side of x equals 2, so it's a point O, F inflection, not a maximum or minimum. Substitute x equals 2 back into the original curve y to get the y coordinate, 9. Stationary point at 2, 9. The second derivative is 0 at x equals 2, so the test is inconclusive. Since die over dx equals 3 times x minus 2 squared, which is at least 0 on both sides of x equals 2, the gradient never changes sign, so 2, 9 is a point of inflection with a horizontal tangent, not a maximum or minimum. Remember our road? Hilltop frowned, a maximum. Dip smiled, a minimum. That shelf, second derivative 0, test failed, so a point of inflection. For the nature of any stationary point, find die over dx, solve the stationary x values, differentiate again, evaluate. Positive smiles, a minimum. Negative frowns, a maximum. Exactly 0, check die over dx's sign either side.